The standard model of particle physics relies on a persistent contradiction. It describes light simultaneously as a continuous wave and a discrete particle, the photon. This duality is necessary because current physics treats the vacuum of space as an empty geometric stage. It is considered a void for objects to travel through. But describing a photon as a massless projectile creates a mechanical paradox. A discrete object with zero mass cannot physically carry kinetic momentum through absolute nothingness. This contradiction isn't necessarily a profound mystery of nature. It is the expected result of using a mathematical model that is missing a physical component. By accepting a massless particle in an empty void, physics trades mechanical cause and effect for pure abstract geometry. In a 2026 paper, researcher Menelaos Georgiadis proposes discarding this empty void framework completely. He models the vacuum as the plenum, a hyperelastic, solid, continuous medium. In this framework, light is a pure transverse mechanical oscillation of the space itself. The Elastic Continuum Theory strips away quantum abstraction. It attempts to derive standard quantum properties directly from solid continuum mechanics. Modeling the universe as an elastic solid removes light from the realm of abstract duality and anchors it strictly back into physics. To define the mechanics of this medium, we use a 4-vector displacement field, tracking every point in the solid lattice. The foundational axiom is that the universe behaves as a hyper-rigid solid, absolutely resisting any change to its total volume. We impose the incompressibility gauge. Mathematically, this vanishing 4 divergence prevents the displacement field from expanding or contracting in volume. Because the medium cannot compress, longitudinal pressure waves cannot exist. The nodes physically lock up and reject the deformation. Any mechanical wave moving through this vacuum is forced to oscillate perpendicularly to its direction of travel, creating a transverse shear wave. This geometric limitation allows for exactly 2 transverse polarization states. Because the displacement field u is a vector, it possesses 3 degrees of freedom, the defining trait of a spin-1 particle. By physically locking the longitudinal state through incompressibility, only the 2 transverse vibrations remain, which are the exact polarization states observed in electromagnetic radiation. Scaling up from the subatomic structure of the lattice, we can translate these solid mechanics into macroscopic classical electrodynamics. The equations formalized by James Clerk Maxwell dictate the behavior of electromagnetism. Georgiadis derives them by mapping the standard electromagnetic potential directly to the elastic displacement field of the plenum, scaled by a coupling constant. This means the electromagnetic field tensor, the math used to calculate measurable electric and magnetic fields, is exactly equal to the antisymmetric strain tensor of the solid lattice. In continuum mechanics, this tensor measures specific local deformations, the twisting and sliding, or torsion and shear, between the structural nodes. The homogeneous Maxwell equations do not require independent physical forces. They are trivially satisfied as the geometric Jacobi identity of this antisymmetric tensor. By taking the 4 divergence of that same tensor and applying the incompressibility gauge, the inhomogeneous equations, Ampere's and Gauss's laws, emerge exactly. Classical electromagnetism is the macroscopic continuum mechanics of the void. In special relativity, the speed of light, c, is postulated as an empirical universal speed limit. Albert Einstein treated this limit as a foundational geometric rule of spacetime. In the elastic continuum, c is a derived mechanical property. The phase velocity of a transverse wave in a solid is calculated by this equation. The velocity is strictly dictated by the medium's baseline density and its shear modulus, the physical tension resisting the wave's deformation. The vacuum restricts velocity, not because of temporal geometry, but because a physical lattice has a maximum rate for transferring strain to adjacent structural nodes. The model's validity rests on its ability to explain the photoelectric effect, and specifically how energy is quantized, without invoking discrete photon particles. The concept of quantized energy relies on Max Planck's quantum of action, represented mathematically as h. The Elastic Continuum Theory discards the standard explanation that light transfers this energy as indivisible solid projectiles. Electrons are trapped topological solitons, tangled knots within the continuous lattice. The knot is bound within an atomic potential well. Here, the Planck constant h is the exact minimum mechanical action required to complete one full topological phase rotation to untie this knot. Because the electron is a continuous structural knot, it is immune to fractional deformations. It can only change its kinetic state by absorbing a complete integer quantum of action. When a transverse light wave passes through the electron, it transfers elastic shear energy to the structure. If the incoming wave has a low frequency, it lacks the necessary local strain to untie the soliton. The knot wiggles, but the local restoring force keeps it firmly trapped. Detachment strictly requires a full integer quantum of topological action. When a high-frequency wave strikes, the mechanical strain reaches the detachment threshold. It instantaneously overcomes the restoring force and ejects the untied knot. This instantaneous geometric threshold causes a discrete transfer of kinetic energy, generating the exact results of a particle collision. By replacing the empty void with a continuous lattice and defining electromagnetism as structural strain, the elastic continuum resolves the wave-particle paradox. Light operates solely as the transverse mechanical heartbeat of the universe.